second sheet, Mathematics 2. It's called 7.2, and well, let's look here. It's a short one this time. Just a few exercises about Taylor series. The first one is sort of an introductory example, also asking for the convergence radius or radius of convergence. Well, the Taylor series is nothing else than an ordinary power series, but the specialty here is that the so-called Taylor theorem, which is seen here, is used to construct this series out of, or let's say, starting from a given analytical function. That's what you usually have in this case, right? So here, f of x equals sine of x, and also g of x equals cosine of x, two different functions to be expanded to their Taylor series, means that you, by using this well examined theorem, to find that power series which represents the given function in an optimal way. Now, also what we decide here is to do all to perform this this whole operation at x null equals 0. So that will be our expansion point. This is not obligatory, but it's just the usual procedure. Okay, if nothing special is given, you just decide to expand your series at 0. Now, that means that's the reason why there is no subtraction of any other value here from x by constructing these polynomials. Well, looking here, we have to find sort of a scheme by which the derivatives of the given function present themselves. Is there any pattern you can find? And in this case, we know there's a pattern because there's even a cycle when differentiating. Let's just do it. So f of x equals sine of x, which is also, please remember, the derivative number 0. So the function itself is its own derivative in quotation marks. If you say there's the first derivative is next, but derivative number 0 is the function itself, okay? But the first real derivative, of course, f prime of x equals cosine x, that's what we know, and the second derivative equals negative sine of x, which we just had just before in the exercise, the last one from last sheet. Now, and f number 3, you see, prime, how do you say triple prime, right? F triple prime of x equals negative cosine of x, and then the fourth derivative equals sine of x again. This is the cycle we know about when differentiating sine of x. So it's you could say a 4 cycle. Much the same happens when starting with cosine. Also there you have a 4 cycle. So anyway, we do not have to proceed because we know it goes on and on afterwards. So my notation is for Taylor series with the expansion point as an index. So Taylor series at 0, that's just my short notation, of x for f. I should actually I should perhaps put f somewhere to know that it's the Taylor series for the function f, but I don't do this. I just leave it away. So I sum up n equals 0, approaching infinity. I get the nth derivative at x0, at x null, I wanted to say, which is 0 in this case. So I have f derivative number n of 0 divided by n factorial and then times x power n. That's nothing very special, but we have to insert. So f of 0, which is also derivative number 0 at the expansion point equals 0. That's what we have because sine of 0 equals 0. Also the first derivative, which is the cosine at 0 equals 1. Cosine of 0 equals 1, as you all know. And the second derivative, again, because it's the negative, sine of x equals 0, and then the third derivative at 0 equals -1. This is the negative cosine. That seems to be quite an easy scheme. We see that, or we find that all the even derivatives here, you see, all even terms also in the end will vanish in this series. With even terms, of course, I mean all the powers of x which have an even exponent. On the other hand, the odd terms, yeah, have an alternating sign, obviously. It's easy to predict that when I take the fifth derivative, I'm with a positive sign again, and so on, okay? So I have 1, -1, 1, -1, and so on. So that's it, and we can write down sine of x equals, using the formula now, and always please taking care of dividing by these factorials, putting it here, since the even terms vanish, remains f prime of 0 over 1 factorial times x power 1 plus f triple prime of 0 over 3 factorial times x power 3 plus, and then so on, f fifth derivative of 0 over 5 factorial times x power 5, and so on. And now we've already seen that we get this alternating sign here. So all that remains is, as before, by the way, but this is quite a different approach to find the power series for sine of x. But it's nice to see that it agrees with the last exercise from the previous sheet. We get, since this is 1 over 1 factorial, so it's a factor of 1, we get x as a linear term. We get a negative sign here, it comes from here, you see. And so we have -1 over 3 factorial times x power 3, and then we get positive again, as I told you, the reciprocal of 5 factorial times x power 5, and we have our alternating sign. That's an odd function, very important feature. It only carries terms with odd exponent, and you all know this means if you replace x by -x, the sign of all these terms will change, so the function value changes to its opposite. And that's what we have when there is a point symmetry to the origin. That's, of course, a very important feature. So now this is the closed form again, which we already had, which we also had before. And then about the convergence. You remember from last session that we have often used this special formula for, well, which goes back to the ratio test about convergence of infinite series, you remember? So, but please take care that when calculating the convergence radius, you have to put this ratio tails to heads. Okay, so that means you always have an element in the numerator and its successor element in the denominator. That's what we have. Now it's a little tricky here because actually we do not have a complete power series since all the even terms vanish. So I would have to be honest, I would have to take a little longer journey to reason why I may anyway use this method, because I jump over one element which is 0. Just believe me. Also, you can, if you want, you can show that this power series is part of another, a more complete series, also the one for the exponential function, which has a convergence radius of infinity against approaching infinity. So there are several independent reasons for this to be true. Anyway, if we do so, we would see that the factorial, can you roughly understand where this comes from? If I take coefficient ak, I would get, the sign is not important, you know, because of due to the absolute value signs here, but in the denominator, I would get 2k plus 1 factorial, just remember for a moment, and then I would take the ratio, and below I would take the next coefficient, which is then, if I increment k by 1, is something about the reciprocal of the next factorial, of the next odd number. If you know what I mean. If I increment k here, I get k replaced by k plus 1. But please note that the factor of 2 is strong. It means 2k gets replaced for 2k plus 2, and then plus 1. So this is 2k plus 3 already. Okay, just let me take a little note. It's like having, in the nominator, I would get 1 over 2k plus 1 factorial, and the whole thing divided by 1 over 2k plus 3. This is the next odd number, factorial. And then I would, of course, simplify this to be, let's go here now, to be, you know what I mean, fraction by fraction. So that's easy. I get 2k plus 3 here, factorial, and then divided by 2k plus 1 factorial below. And now the important fact is that everything inside here is also contained here. All the factors, because this is a lower number, and except for the upper two factors, which remain. So what remains is this factor of 2k plus 3 times the previous number, which is 2k plus 2. Now here, even numbers are inside, of course, right? So for an example, it's like if you get, it's always good to take an example. If you have 7 factorial over 5 factorial, everything that remains is 7 times 6. You will all know that, okay? Because 5 factorial is completely contained in 7 factorial. All that remains are the largest and the second largest factor of the numerator expression. So that's what I'm using here implicitly. Okay, let's just swipe it out and then proceed. In the end, this is a product where you can immediately see that it's by the way, it's always the case if you have reciprocals of factorials. This is a coefficient series which drops so extremely fast that it's quite obvious that the corresponding series will converge everywhere for any value of x. So that because this approaches infinity. In the end, you could say this method of representing the sign of x like an approximation, even if you cut it at a certain stage, is a method that works fine for any value of x. So B, the same for cosine. Now I have for fun, I have a special idea. I would propose that this time we use term-by-term differentiation, which is always allowed if you have a convergent power series. You can always differentiate and even integrate it term by term to find another valid power series. By the way, the convergence radius always is conserved by these operations. That's also part of a theorem which has been proven. Now, g of x equals cosine of x, which is, by the way, the first derivative of sine of x. And so, using the well-known differentiation rule for our power terms, I do this when just differentiating this series implicitly. I can also do it by hand if you want, because let's look here. So what I have is this here in parentheses, then the whole expression prime. What do? X gets differentiated to be 1. That's easy. Linear gets constant, right? Then cube term, factor of 3 comes here. You see, I get 3 times x squared, but the 3 over 3 factorial means that I can just cross out this factor of 3 against the one here. So what remains below is just the factorial of 2, like 3 divided by 3 times 2 times 1, what remains is 2 times 1 in the denominator. So that's easy. The next one, negative sign remains, of course. The next one then, 5 as a factor and then over 5 factorial. The same effect. 5 is the biggest factor inside this factorial, so you can cross it out and replace this one by 4 factorial. Also, don't forget, the exponent gets reduced by 1 here and here. So it's very nice to see that every single term here, you could say, transforms to an even term. So even the linear term gets to a constant. And also we can see that the cosine of 0 then must be 1, because all the other elements will disappear if I insert x equals 0. And you see that this is an even function. And it's also it also has an alternating sign, which is a strong hint at the fact that this is a periodic function, like a wave function. It is, right? And so this is what we get, and we can also put it in closed notation. It's a question of training, yeah. This is the manual method, which is good for your first time. But it's not really a problem to do this in one step using the summation notation. You see here, because this is a scheme that represents any single term of the series. You should, of course, always take care for the 0 element, which sometimes needs a special consideration. But in this case, it even doesn't need a special consideration, because when k equals 0, I have my linear term here, which gets differentiated much by the same rule here as all the others. So what do? We just take this exponent as a factor, which then, like we've seen before, which then cancels against the highest factor of this factorial. This one transforms to its predecessor factorial. The sign is conserved as it is, and the exponent shrinks by 1, so that in the end it's x power 2k, and that's all. And I think we should not have to change the counting here, as I argued, and indeed, that's what you get. What I just told you. That's even nicer, we could say, a little simpler. The appearance is a little simpler than before. So now this is the official summation form of the Taylor series of cosine of x at x equals 0, convergent also for all x element r. As I told you, the convergence radius remains unchanged when differentiating term by term.